Course 1, Lesson 58 is going to introduce us to what might be a new topic, probability and chance. The goal isn't to become masters of every possible outcome and probability scenario this year, but we're laying a foundation so that we can become masters in later years of math. We live in a world of uncertainties. You hear things like, what's the chance of rain? What are the odds of winning? What's the probability that I roll a number needed to land on the winning space in my game? Probability helps us assign numbers to uncertain events and compare the likelihood that various events will occur. In what few scenarios where you can know it's going to happen, the probability we say is 1. Probability is 1. Such as, I have a dice, 6-sided die, I'm going to roll a number 6 or less, right? Probability of that is certain, it's a 1. Or I'm flipping a coin and I'm going to flip either a heads or tails. There is no it lands on a side outcome. That doesn't happen. Probability of landing on either heads or tails is 1. 0 is assigned to a probability that is certain to not happen, such as rolling a 0 on a die or getting heads and tails when flipping a quarter. So most events fall in between these two. That's why when measuring probability, we use a decimal or a fraction, such as flipping a heads or tails. If I'm saying my probability of flipping a heads in my one flip, that would be 1/2 probability. See how that's a fraction? It's between 1 and 2. Or maybe the likelihood of winning a basketball game would be 1/2, kind of, because there's 2 teams. If you have 4 teams playing that night, the probability of winning maybe one game is 1/4 or something like that. You get the idea that probabilities are set between 1 and 0. They're always a fraction in between those. So, I really like this picture. It shows what we were talking about, and everything up to a half is fairly unlikely. Everything above a half between 0 and 1 is likely. We're going to practice assigning what a probability would be for various events. The set of possible outcomes for an event is called the sample space. Flipping a coin once, the sample space would be you get either heads or tails, all possible outcomes. Sometimes we abbreviate heads H and tails T. Look at the spinner down here and notice how not all outcomes are equal. Which letter are you most likely, can you tell? Most likely of the 3 to land on? Well, the one that's currently landed on, right? The A. Why? Because it's twice the size of B and C. But if I asked it like this, what are you more likely to land on, B and C or A? It'd be the same, because added together, B and C are just as likely as A, as long as it doesn't matter B or C. B and C have the same area, so landing in either one is equally likely. While A has the largest area, we can expect the spinner to land in it more often than just B or just C. What's the sample space for the experiment? To me, the sample space would be A, B, or C. Those are our possible outcomes that we could land on, right? Are the 3 outcomes equally likely? Well, we talked about that. No, A is more likely because it's got the larger area. B and C have equal outcomes because they have equal areas. Now think about how these are all related. The size of the sectors in relation to the circle. How much of the circle is letter B? It's 1/4. So in terms of probability for letter B, I would say because the area is 1/4, I would actually also be able to say that its probability is 1/4. And the probability of C is 1/4. Whereas A looks like half of a circle. These are actually directly equal they're fractions of the circle. Because a circle is 100%, or 1 over 1, we need to be able to add up all possible outcomes in the sample space. It must equal 1. All outcomes possible in the sample space, when added, should equal 1. Just like we learned with pie charts, all outcomes should end up adding up to 100%, or a full circle. And 1/2 is really 2/4, right? So I'll rewrite that one as 2/4. So adding 1 plus 1 plus 2 is 4. 4 plus 4, well, common denominators, you don't change. 4 over 4 is the same as 1. So you can see, adding all outcomes, you can show it in decimals too, should equal 1 in the sample space. If we spin the spinner a large number of times, we expect about half of the spins to land on A, about a fourth, or about 25% of the time, to be on B, and about 25% of the time to be on C. It's just logical, right, if you think about that. Can I know it's going to land on A, let's say out of 20 times, 10 times? No, but that would be the most likely prediction. But you can never know, because the world doesn't quite work predictably that way, right? Meredith spins the spinner 28 times. It asks how many times can she expect to land on A. Can she expect? Not know, but expect, right? That's the thing about gambling. You can never know for sure. Well, half of the time, we said, is A, because it covers half the circle. So half of 28 times is 28 over 2, or we could have just gone right to 28 divided by 2. So 14 times we'd expect to land on sector A. Now sector B, we said, was about a fourth the size. So this is going to go for C as well, right? These each have a fourth of 28's likelihood. So 28 divided by 4 is 7. 7. Double check that this is right. Add them up. 7 plus 7 plus 14. Looks like 28 to me. So we divided by 4 to get how many times for B and C. A we divided by 2. So Meredith can expect the spinner to land in sector A about 14 times, B about 7 times, and C about 7 times. Hopefully that's making some idea of a sense. A weather forecaster, in the language of percent, we expect the spinner to land in sector A. We use 50% of the time, right? Same as a half. We expect it to land in each of the other sectors roughly 25% of the time. When we express probability as percent, we call it chance. When do we call it chance? When we talk about percent chance, not fraction probability. For fraction probability, percentage chance. Got it? A weather forecaster says 60% chance of rain. Find the probability then. Probability, we said, is fraction. So they show 60%. How do we make it a fraction? You put 60 over 100 and reduce to 3/5. Or you call it 0.6, 6/10. Both would be ways to show the probability. Last thing, complement with 2 E's. Complement of an event is the opposite. So if I'm looking for heads, the complement is tails. In the chance of rain scenario, the complement of rain tomorrow is it being clear, no rain, and the probability of that would have been 40%. The rest of 1. There's no in between. That's it. So if you add up the outcome you're looking for with the probability of the complement, that adds up to 1. To find the probability of an event, we simply add the probabilities of the events that make up the event, of the outcomes that make up the event. If all outcomes of an experiment or game have the same probability, then the probability of an event is number of outcomes in the event over number of possible outcomes. That's if all outcomes have the same probability, such as rolling a die, looking for the number 4, Or even find the probability that the upturned number is greater than 4. Then find the probability that the number is not greater than 4. The way we do this, number of outcomes in the event over number of possible outcomes. So basically, on top we put what are we looking for, and in this case it was number greater than 4. Well, that would be 5 and 6 on a die, so there's 2 outcomes we're looking for. On the bottom, all possible outcomes for the same event. Well, there's the 2 I'm looking for, and then there's 1 through 4 as well. There's 6, if you add it together, 6 total events when rolling a die, right? Rolling 1 die, there's 6 possible numbers, 2 of which I'm looking for in the probability. We reduce that to call it 1/3. Now, what's the probability that the number is not greater than 4? Well, that'd be 1, 2, 3, 4. 4 numbers, still 6 outcomes. That comes to 2/3 is that second one. Number of what we're looking for over number possible. If a bag has 5 marbles, 4 red marbles, 4 yellow marbles, 2 green marbles, and 1 orange marble, without looking, Brendan draws a marble. What's the probability of drawing red? Well, we're looking for red. How many reds were there? 5. That's what goes on top. What's the number of possible outcomes? 5 plus 4 plus 2 plus 1, 12. If you add that all together, 12 possible. So our answer here is 5/12. Can I simplify? No. What's the complement of that event? I would say 7/12. Everything else, these added together should equal 12/12, or 1. Because the probability plus its complement should equal 1. So you just put the opposite amount. What is the probability of the complement? I guess I just answered that. What was the probability is 7/12. The complement would be drawing a yellow, green, or orange marble, right? Probability and chance. They said the complement is not red. Same thing. So let's do D through G, please, for your practice to show me. Thank you.